Graphs are widely used to model the structure of systems across fields like bioinformatics and social networks. Subgraph isomorphism, or SI, is a key problem in this area, allowing us to find patterns in graphs. While this is well studied for static graphs, many real world applications require dynamic analysis where graphs evolve over time. Oberoi and team address this critical gap.
So the problem that was addressed was Oberoi and his team was that the problem of subgraph isomorphism in dynamic graphs, where the goal is to find patterns that change over time. Most current methods combine all the data into one graph with timestamp edges. This approach misses important details about how the graph evolves step by step. Oberoi's team created an algorithm that looks at graphs as snapshots in time, making it better at identifying patterns while keeping the timeline in mind. So their solution builds on an existing algorithm known as the VF3, originally designed for static graphs, and adapts it for dynamic graphs by first matching nodes and then checking connections. This method respects the order of the snapshots, ensuring it captures both the structure and how it evolves over time, which is important for problems where the sequences of change matter. For example, when we observe the development of proteins or when analyzing social networks. So his solution is better than others because when their algorithm was compared to two popular ones like Mackey's algorithm and temporal array using real data sets like email communication and social networks, Oberon's solution worked well as a temporal array for larger graphs, and it did better than Mackey's algorithm, which often failed due to memory issues. It also scaled better in cases where existing methods could handle the snapshot-based approach, making it a good choice for specific real-world problems. Furthermore, it had latency reduction and it was energy efficient as it reduced power consumption. And when practically tested, it produced results which were better as compared to the other algorithms. Okay, Mamuna, over to you.
Okay, so now I'll execute the code. Okay, so as we can see, the algorithm successfully identified one subgraph match with node mappings aligning with the expected results. The runtime 0.000182 is efficient, supporting the claims of practical performance. Okay, so the code takes two inputs, a pattern graph H and a target graph G represented as snapshots, where each snapshot contains nodes and edges. The code outputs the matched subgraphs, node mappings, and execution time. For example, if H includes nodes V1, I5, and R3, and G contains nodes V100, I15, and R25, the code maps each node from H to G while maintaining the order in which the snapshots occur over time. Here, the output 80V1 maps to G0V100 shows that node V1 in H is mapped to node V100 in G. If no match is found, the output indicates that as well. This allows users to see whether the dynamic graph pattern exists in the larger graph and how it aligns over time. Over to you, Fatma.
Bourgeois introduced a temporal passing network model to study team dynamics in basketball. Figure 3 shows that the Spanish team exhibited higher graphlet entropy, meaning that they had a wider variety of interaction patterns, making the gameplay more adaptable and unpredictable. In contrast, Argentina used simpler graphlets like 1 and 1-2 more frequently, which made their play style more predictable. Figure 4 illustrates the transition profiles, with Spain demonstrating greater entropy and adaptability. This higher complexity in Spain's interactions contributed to their unpredictability and eventual victory. The findings emphasize the value of entropy based measures in understanding and improving team performances.